Hello, everyone. Welcome to the fifth webinar in the Joint TranSET webinar series, which will cover a variety of research projects related to innovative technology, techniques, and processes in transportation infrastructure inspection. It is the counterpart to our previous webinar that was on the same topic. My name is Chris Malson. I'm the program manager of TranSET, which is Region 6's University Transportation Center, or Region 6's UTC. This webinar is jointly hosted by us, by TranSET, but also by Region 7's UTC, the Mid-America Transportation Center, which is led by the University of Nebraska-Lincoln. Today, we'll have 4 20-minute presentations, and we'll save the questions until the end of the 4 presentations for a quick 20-minute group Q&A. So without further ado, I'll introduce our first speaker, Dr. Salam Ramatalla. Dr. Ramatalla is a professor in structures, mechanics, and materials at the Civil and Environmental Engineering Department at the University of Iowa. His field of interest is in the area of mechanical vibration and its effect on the health condition of structural, mechanical, and biomechanical systems. Examples of his research studies include the effect of operational loading on the integrity of highway bridges and the biodynamics of human transport interaction under whole body vibration.
Thank you, Chris. Thank you, everyone, for attending this presentation. Again, my name is Salam Ramatalla. I'm a professor at the Civil and Environmental Engineering in the University of Iowa. On this project, I have also Dr. Corey Markford. He's assistant professor and he's a co-PI on this project. And Ali Karimpour is a graduate student working toward his PhD. As you can see, the title of this presentation is Infrastructure Inspection During and After an Unexpected Events. And so what you see here that we have challenges from natural events. And when I mention natural events, that could be flooding, could be hurricanes, could be earthquakes. However, the focus of this work would be more on the flooding because of it's relevant to what's happening frequently in the Midwest. And you can see with the challenges here that these natural events will really put a lot of stress on the transportation system, especially on bridges. And you can see that sometimes we have failure, complete failure, we have partial failure, and sometimes we don't know what's going on. So for example here, during the event, there is a lot of stress is applied by the river on the bridge. And that's what really brings the question is that with this situation, can we allow a truck holding like hazardous material to cross that bridge? Is it safe to do so? So the goal of this work really is to develop like a computer model that help the emergency responder and people with decision making to make this hard decision. And one thing I want to mention here, with the flooding, it's very, situations can become very complicated because you can see here, sometimes the forces is not only coming from the river, but it's coming from other things. For example, fallen trees and the other objects, and also it is not only structurally affecting the bridge directly, but also underneath the on the river ground, and there we have the scouring, and that will affect the load capacity of the piers. Now, this project will not really consider scouring. The idea here is that we're going to look to the superstructure and see how it's conditioned before and after the events. So in this event, there are always challenges to emergency responders. So before the events, for example, if we hear in the news that with the forecasting, there is like a big storm is coming, and it will be great if we know how that storm will affect the water level and the amount of water in rivers. If we know that, then we can already, we can use a computer model to predict what will happen with this situation. And with that, how much load that water generated from this storm will apply to the bridge, and what's the bridge loading capacity. This is like a pre-planning. Now, when the event comes and we have a flooding, and then during that event, we want to, emergency responder will be really great if they have information as to what's going on the bridge. Is it still standing there? It has partial damage. How much load it can carry? And all these questions, it will help the emergency responder to really do planning for logistic and safety. And after the event, of course, if we have so many bridges, and if the storm has like a wide effect, that may affect so many bridges. And then the question would be, I want to start the repair after the events, and then where I should start, here or here, and what's the priority of these bridges and their condition. So the goal of this work, again, is to develop a computer model to predict bridge loading capacity before the flood. In this case, if we gather information from forecasting, and here really we're lucky, we have the Iowa Flood Center, they have all this information, and they can tell us where the water level and volume of water in this river will be that much. And then this information will be nice if we have that, and then the computer model will predict the forces that can generate from this types of flooding. And then after that, we have the model, which is a finite element based model, that will tell us how much if there is damage on the bridge, and then how much the loading capacity. Again, as I mentioned, this is before, but during and after the flood, this is really become more challenging, because there are other forces in addition to water, as I show you in the first slide, when we have like fallen trees and objects. And these will really generate forces that we cannot predict, because they are random events. So it will be nice if the computer model will get some measurement from the field. So if you put some sensor on the bridges, and that will always give us real-time data to what's going on, and this will really enhance the model capability in predicting more accurate results. And our long-term goal is really to change the map of Iowa Flood Center. And I don't know how many are familiar with this, but last time there was a presentation about this. And this map, they have so many maps, but basically this map is telling us that's the flood condition, and it's all graphic. And if we can change that graphic to physics-based, that would be great. I mean, goal. Now, the University of Iowa is really well suited to conduct such a multidisciplinary project, because really we need background with structural health monitoring, fluid structural interaction, and weather forecasting, and flood prediction, and the facilities. And we have all these components here at Iowa. So for example, Iowa has the Iowa Flood Center, it has the hydraulic lab, and has a center for computer-aided design. To that, we have we have very good experimental facilities that we can tackle such problem. And again, the goal is to provide the owners, bridge owners, with information about the health condition and loading capacity of bridges, so that can make better decision. The Center for Computer Design, we have here we have really a shaker table. We can put a structure on this shaker, and we can simulate different types of loading, vibration. And for example, this is an earthquake, a simulation of an earthquake signal. With this Center for Computer Design, we also have different types of motion sensors. We have different types of force sensor and pressure sensors. So really, we can, we can deal with this problem, with confidence. And also, we have experience in modeling, so we feel more comfortable doing such a challenging problem. With IIHR, we have different types of labs, and here you can see one of the labs here. For example, this one is like a water flume, where we can generate different types of flooding in this flume. And you can see here, for example, we put a sample bridge here, a small scale bridge, and we did that. Also, we have the wind tunnel laboratory, when we can really, if we want to generate like a hurricane types, or high wind types, like a phenomena, we can do that. But also we have a very nice facility, and that's the facility with Dr. Corey Markford, the co-PI on this project, where we have like the wind generating waves, which is really a very nice, unique facility. But with this project, really, we are focusing on just simulating the flood because it is, as I mentioned, it's widely experienced here in the Midwest. With the Iowa Flood Center, we have, this is really, they have very nice maps. For example, here we look to the Cedar River at Cedar Rapids, and we look to the annual flood time history. And you see this is the time history for so many events, and here we have the cubic foot per second. Now, if the flow in the river is above that number, then we can have flood. Below that, no flood. And then, for example, we have 31 flood in the last 106 years. And this is what happened in 93, when we had the flood in 93. And this is what happened in 2016. And you can see here, 2016, the flow was bigger than 93, but the damage really was less. And this is because of readiness and preparation and more control. And this is what happened in 2008. 2008 was really a very specific phenomena that really the river went beyond what is expected. Now, so what we did in this work, I'll just give you an idea that what we achieved and what we're trying to do. So we started with a highway bridge here. This is a highway bridge from Iowa City toward Kelowna, and this is Highway 1. And this bridge is one-span bridge crossing a creek. And we tested that bridge in 2019, and we thought that, in 2009, and we thought that this is a good start. So we received the plans from DOT, Iowa DOT, and from these plans, we create a CAD model, and that CAD model, then we put it in the computer and generate a finite element model of that. And with that finite element model, also we use 3D printing to generate a scale model of that bridge, and the scale here is 1 to 25. Then what we did, because we have the computer model, and this is really nice with the computer model because you can do a lot of testing with this model and change dimension, whatever we would like to do. And in this case, we apply impact loading, we can apply ground vibration loading, and so forth. And then we can have all the response that we want to see from the structure. So now, look, for example, here, when we did the numerical testing to the FE model, we see this, we call them a mode, and this is how the bridge will deform a certain frequency. For example, here we have 4 of them, 4 modes. Now, this is very important because now, if you have a truck crossing, it has a certain weight and crossing a bridge with certain velocity, and if that truck can generate a frequency that match the frequency of mode 1, say, for example, 5 hertz, then the bridge will deform like this. If the truck can generate frequency that can excite that mode, then it's going to be this. And from here, you can see really very clearly, this truck can cause a lot of stress in this connection between the girders and these cross beams. And so forth, this one, it can affect the abutment. So the point here is that really when we have a finite element model, and if it is, of course, it should be good enough to simulate the real bridge, then we can do a lot of things. And one thing that we want to achieve from here is that can we really have the model that can predict the loading capacity of a bridge under certain conditions. So here, what we did on this bridge model, we did, you can see it here, we put it on shaker and we did different type of testing. And for example, here we put masses on the bridge and we see if we can capture that differences between the healthy and this one, we call it unhealthy. And of course, with that, we created a damage detection method. And what the damage detection method does is that will tell us if there is change in the property or integrity of the structure. Now, also, for example, here with the physical model, we can do a lot of testing. For example, here we change the we lose some of these bolts that may simulate damage at this support. We added masses, and we did all these different things, and we tested the method, and we see that can we really capture damage? And basically, from experimental data, because we put sensor, then we can go to the damage detection method, and the damage detection method will tell us you have failure here, and or this integrity of this support change, and so forth. So this is some example of that damage detection of the physical model. So you see that we have different types of sensors, and here you can see we generated two damage intensity, D1 and D2, and D2 is larger than D1. And you can see for this type of sensing, we can get that, but for this type of sensing, we were, for some reason, didn't work for that condition. So really, there are so many sensors available in the market, but the tricky part is that how to choose the right sensor and where to put the sensor in the right location. Then do you see here we put that as a model bridge inside the water flume, and the problem that the water flume has limited capacity, so we didn't see a lot of changes here because this was too stiff. So what we did, we moved to another bridge. This is in Cedar Rapids, and this is a multi-span bridge. And again, we did the same thing. We have the drawing from DOT, and we created that bridge. And this time, we created a bridge from plastic. And we make sure that we achieve the geometrical similarity, the Cauchy similarity, and the fruit similarity. And what are these similarities? They just make sure that we maintain the same inertia and ratios and elasticity and so forth. And you can see here on the bridge, it has 2 span only, and it has 5 piers. And here we put sensors to monitor what's going to happen to the bridge. And you can see with this method that we developed, we don't need so many sensors. You can see here, we just need 2 sensors to see what's going on here. Normally, other methods, really, we need to put so many sensors to find out what's happening. And now what we did, we measured the response of this bridge in 6 directions, basically in the roll and the like heave and sway and so forth. And the goal with that is that really we want to see how these parameters change during the flooding. So now we tested the physical model on different flooding conditions. So here, if you look to this figure, you see there's just nothing, just a river. It's a normal flow. And here, stage 1, and this is stage 2, and stage 3, where you see here the river is, the bridge is inundated by the water. And with this condition, we try to see, can we capture damage if we under this loading condition? So what we did, we created different type of damage. And for example, here you see we have 5 piers. So we changed the integrity here, and somewhere here on the bridge, and try to see, can we capture this change in the integrity of the structure? And here, this is what we see. So for example, we have 3 types of damage. So you see damage 1 here, damage 2, damage 3. So it's increasing in intensity. And for each time, with each stage, really, we can capture damage. So really, in all these stages, the response was different, but still with that, we were able to identify damage parameters. And from these damage parameters, we basically use a subset of this to capture the damage. So really, our goal is to develop a computer model of a multi-span bridge. And here's the challenge. We have a prototype bridge, a real bridge. We have a physical model, and we have a computer model. And toward the end, we want to use this computer model to predict damage based on information from forecasting before like the events. And this model should get motion sensing or other sensor from the bridge and come to here and then predict what's happening. And then after that, we see, well, how much loading capacity the bridge can take. Now, with the what we want to do later in this project, we want to develop like a computational fluid dynamics model, something like that, where you see the bridge And this is basically how the flooding is here. And the goal is, if we can simulate that to a certain limit, then we can see how much loading this like river or like whatever we have here on the bridge, and that will help us in our decision making. The last thing that we want to really, or one of the last things we want to do is, how can we predict the loading capacity of a bridge under this condition, and how much traffic load we can allow during a situation like this. This is a really very complicated problem, because here you have the coupled loading between the water, the bridge, and the traffic. But this is some more work that we wish, we hope we can achieve, and this is what we are working on this time. So the expected product of this work would be a computer model that can predict loading capacity of a bridge before the events, basically based on information from the forecasting, and then during the event, where we can get some measurement, and that measurement will be combined with the model to predict the loading capacity. And finally, this is the long term, we want to update the Iowa Flood Center graphic data, the one I show you, to physics-based. And with that, I thank you very much for attending.
Perfect. Thank you so much, Dr. Ramatala. I apologize. I should have mentioned earlier, the project that was just presented was associated with the Mid-America Transportation Center. The next presentation is associated with TranSET, and the last two are funded by the Nebraska DOT. So our next presentation is by Dr. Fernando Moreau. Dr. Moreau is an assistant professor in structural engineering at the Department of Civil, Construction, and Environmental Engineering at the University of New Mexico. He also has concurrent appointments in the departments of electrical and computer engineering and mechanical engineering. He's the founder and director of the Smart Management of Infrastructure Laboratory. His industry experience includes working for ESCA consultants for over 10 years, with experience in the design, construction, and replacement of over 30 bridges in the US. His research interests include structural dynamics, structural health monitoring, wireless smart sensor networks, augmented reality, unmanned aerial systems, human-machine interfaces, and aerospace structures design, monitoring, and reusability.
Thank you, everyone. I'm joining this webinar as the second speaker. I'm calling from the University of New Mexico, the Department of Civil, Construction, and Environmental Engineering. And I'm right now in a classroom with 15 students, seniors in the Department of Civil Engineering, that they are following the governor. So it's very educational for our university. This is a picture of the group of graduate students that are working with me on the research that I will present today. They are graduate students in the Department of Civil Engineering, and the contents of this work is being done by them. I have an outline of the presentation today. My objective is to cover the motivation for the augmented reality from the structural inspection perspective. I will define in which context augmented reality can have an impact on transportation infrastructure, and I will show some of the applications that my students are doing in the University of New Mexico. As you can see, there is as most everybody knows, there is a concern regarding the infrastructure in North America from the American Society of Civil Engineers. Yeah, for the motivation of this topic, I was mentioning there is a priority from the American Society of Civil Engineers on addressing the state of our infrastructure. There is a important report card that address what are the actual grades of our different bridges and highways and railroads that exist out there. That grade was created to get the attention of the leaders on the nation about how important it is to keep our infrastructure. Okay, so you can see these different grades that are showing throughout the years, and the grade in general is very low. We have a B+ from 2017. Here at the TranSET Center, we think that research and education go together. So this is a picture of how our students are getting exposed to the report card. This is the blue card from 2017, and we covered the importance of getting them on their senior year before they join industry on the state of our infrastructure from the society perspective. One of the areas that I will be talking today is about railroad bridges and bridges in general, and I wanted to emphasize that there are many approaches for maintenance, and I'm going to be talking about the area of inspections, structural inspections. You can see different inspection sites. Some people hanging from the bottom of the cross beams there on a very long span bridge using a man lift, and some car with a very long boom that goes underneath. And we asked inspectors what is on their experience, what is their number one problem, and they brought us to the area of how can we augment their accessibility and the information that they collect on the field, and that's where we're coming from. We went to use an existing device or tool that has been studied for defense or medical applications, military, and we are trying to implement this augmented reality on the area of structural inspections. What we are using is HoloLens from Microsoft. This is a wireless device that we've been using for 2 years, and our strong collaborator in Los Alamos National Laboratory, picture here on the bottom right corner, David Mascarenas, is our companion on this adjustment of augmented reality for structural inspections. Just very briefly, so the people on the audience can get familiar with the hardware software opportunities for, and basically I will mention on the webinar, it's a programming research. So basically, you need to program code the applications that assist your structural inspection. So I wanted to make that very clear for those interested on this area. We believe on layering information, such as we do in computer science. We believe in assisting the human to be an Iron Man, Iron Woman, where they can assimilate knowledge much faster. And we want to share that information. I should point out that the last issue of the American Society of Mechanical Engineers, they start their article on AR with the main character of the Iron Man movie. That's the current issue of ASME. And for the rest of the presentations, we have some of the applications that we've been developing in the area of transportation infrastructure inspection. The first video here shows measuring linear distances. We identified that this hands-free collection of distance between, it could be gusset plates. This is a small bridge that we have here on our structural laboratory where without using the tape measure, you can click in your points of interest and collect direct distances. Imagine you are climbing on a bridge around water, or maybe inspecting any other tall concrete structure. You would need to separate your hands from the whatever you are securing to and collect these distances. And we benchmark the accuracy of this measurement. And here you have the table with a matrix 1 to 12 and about 20 feet distance, squares of 2 feet, and errors in the top on the bottom right corner. You can see there the maximum is in box 9, which is 3%. Everything else is 2% or less. So we're very satisfied with these results. Secondly, we developed a crack length measurement issue. Here we have one senior in the Department of Civil Engineering, Somi. She used to work for the New Mexico DOT, and she's collecting the traditional crack inspection method in the Center of Research and Advanced Computing here in UNM. We are timing. She's collecting this crack of 3 lengths. In reality, she has to move her ladder. It could be a much taller ladder to complete her task of documenting the crack lengths. We have a total summary of moderate or high risk because the inspector has to go up and down on the ladder. You have to carry the measuring tape. You should also include even the accuracy. We say good, it could have some variance depending on the inspector, and the time was 33 seconds. Now, let me show you how would the inspector conduct this inspection with augmented reality. We are timing the same crack, and in this case, the ladder is not a factor for her inspection, and she doesn't even need to touch the wall. She's clicking on the top right corner, the different measurements, and it's being added as she measures. She doesn't need to remember what was measured. The summary is the risk is less, the accuracy is probably better if you remove the variability, and the time 12 seconds. In summary, augmented reality can benefit the safety, the speed, and the accuracy of the bridge inspectors. Then we move to the area measurement. It could be that your transportation infrastructure, such as highways, demands various field measurements for areas takeouts, contractor payment, and such. And we conducted again this research with Los Alamos National Lab and Los Alamos County in New Mexico. The Los Alamos County, because they're managing their transportation infrastructure, were interested that we demonstrated how accurate was the area measurement using HoloLens. So they could replace their survey crew of 3 people on the total station with one inspector equipped maybe with their HoloLens on their backpack, going to the area in question and measuring the area. And we have 3 areas. This is the data acquisition in the Los Alamos County. We did this with the county because we want to hear from the owners of the infrastructure how practical our research is. So basically, one student of the civil engineering department was working in Los Alamos County, supported by the Los Alamos County, investigating the applicability of this research. And the students in Los Alamos National Lab, the Los Alamos County staff, we 3 together investigated if we can measure areas of interest for the owner with augmented reality. And as you can see, you just walk around, select the points, X and Y. The computer is creating this 3D mesh of data that you can use for your area calculation. It takes basically a couple of minutes. I will continue, but you can see it's a very straightforward data acquisition. The point is, it's an irregular shape, otherwise you should need a total station to get your X and Ys. The results were astonishing. On the first column, you have the survey data for the 3 areas, 187, 147, and 129. And on the second column, the HoloLens average measurement, 190, 149, 127. The errors, in summary, were under 2%. The Los Alamos County was satisfied with this error. They even questioned if, because of the cloudy day or the location of the stations, the error is negligible from their perspective. The other application we have here is related to bridge impact. This is a video from 11foot8.com. You're going to see a track impacting that bottom flange. As you can see, you can go to the website. It's a common event that happens there frequently. What we were thinking, if we can inform the inspector after that impact about how severe was the impact, we could conduct the inspection more quickly and with objective data. So we validated this experiment with the Chinese Earthquake Administration. They collaborated in creating a small through-plate girder that we tested through lateral impact, and we conducted some impacts on the lab. As you can see on this experiment, we impacted a crash beam that is meant to protect the bridge. Here is a high-speed camera and matches low speed. So the protective beam is intended to protect the bottom flange of that bridge, so you don't need to stop the trains after that impact. The problem is you still need to inspect the bottom flange. What we propose is to conduct augmented reality inspection right after the impact. And here we are collecting a triangulation after the impact. As you can see, we have highly monitored infrastructure on the lab to compare and validate are algorithms with the LVDTs and strains that the students install prior to the experiment. And the 3D mesh is collected, and we can compare the 3D mesh before and after the impact. In this experiment, I actually climbed to the top of the bridge because I wanted to demonstrate that you can also climb with a hands-free device. So even I'm carrying my HoloLens, my hands are free, so I can come here to the columns there on the laboratory, go up. I don't need to get my hands are free while I'm collecting this 3D mesh data. These are the cross beams. The students installed Xinxin, put all the strain gauges on every cross beam. There were 33. So we have, we can validate our augmented reality. And here are the 3D point cloud that we created on the before and after. You can see the green before and the gray after. So clearly you can see how the crash beam stayed on the original location, came in a little bit, so you can see the one before. So you could compare the volume between the two. The other application, we were communicating with a large amount of data that we want to access on the field. And the students developed a hardware added feature with the Los Alamos National Lab where we could scan barcodes. In this case was for the interesting to access PDFs on the site. So you don't need to open your computer. You don't need to bring your drawings to the field. That would be a very useful application. And this is a short video where you can see the actual collection of data. Here, the student is showing the 12 possible barcodes. These were 12 canisters for our experiment, and he will select number 5. So what will happen is that when he clicks on the barcode, he collects the barcode with his device. The reading is successful, and he will send that barcode remotely to the computer, to the data, to the server on the computer. So it's not on the HoloLens. It's connected through internet. And once he finds that code, it's going to look in the server for the information of interest. In this case, was some interesting information inside that canister. So in that case, you could see how he could access this information. Finally, the last application that I wanted to show you is how we can collect strains and accelerations of your systems with sensors, and you can obtain the readings of those sensors in real time. We are using sensors that the students fabricate here on the Department of Civil Engineering because they are interested in developing the hardware and the software of physical infrastructure. This is a short video that demonstrates how their project works. And the first example, you see the strain gauge on the left-hand side is built by the students on a steel design that they did last year. So they are capable of developing very practical and sophisticated tools for steel strain measurement. You can see how they added a weight of 500. The strain went down to on the vertical axis, and they added a weight 1,000 grams. So it's 3 times this value, and you can see the strain reducing proportionally. So their application was very successful, as you can see. So what I have here as a conclusion is the value of this research to assist the prioritization, which is a need of the bridge inspectors, objectively informing the bridge inspectors with higher safety, less time, more accuracy. We believe at this project from TranSET and in general as a center and as a PI of this project that this human infrastructure new interface can benefit the entire nation, and we were talking about the infrastructure report card. We have been sharing this in many events. I wanted to have 3 slides here to show you the impact of this research. This is the open house that will happen in UNM on Saturday, and they chose the TranSET project to announce engineering. So we felt that TranSET has a big impact in our university. This is a workshop that we conducted with the New Mexico Department of Transportation at their request. These are 12 bridge inspectors, and we share the application of this technology on their interest. And we are working together with them in conducting new research that is practical for their operations. We have another webinar prior to this one that was in December, where we have also shared the early results of this TranSET project. It generated significant attention. With this, I wanted to thank the various collaborators that have assisted this project. Thank you for your attention.
Thank you, Dr. Moreau. I'm glad your students were able to join us. So our third speaker is Dr. Jinying Zhu. Dr. Zhu is an associate professor in the Department of Civil Engineering at the University of Nebraska-Lincoln. She received her doctoral degree in civil engineering from the University of Illinois at Urbana-Champaign in 2006. Her research interests include non-destructive testing for concrete, wave propagation, cement material characterization using ultrasonic waves, and innovative sensing techniques. Her research has been sponsored by multiple state and federal agencies, including the Department of Energy, Department of Transportation, and Department of Defense. Dr. Zhu is a recipient of the ASNT Fellowship Award in 2012 and a four-time winner of ACI James Instruments Award. She is an associate editor of the Journal of Non-Destructive Evaluation.
Thank you, Chris, for the introduction, and I'm glad to have this opportunity to share our recent research findings. So this presentation's topic is on the development and implementation of a moving NDE platform for bridge deck inspection. And I have my colleague, Dr. Chen-Wu Sim, and collaborator from Brigham Young University, Dr. Maziel and Dr. Guffier. Okay, so before actually I talk about this research project, I want to first show you two related research projects also sponsored by Nebraska DOT. And one is about development of an automated acoustic scanning system. Another one is for the GPR data collection and the data analysis for bridge deck with asphalt overlays. And then after that, we realized the different types of NDE data actually give complementary information. And if we can synchronize this data collection and with the positioning data, and we can improve the accuracy of the condition assessment. And so that's the motivation we want to develop a low-cost NDE platform. And then so the next step actually is our ongoing research project. Currently, we are focused on data analysis and data fusion from multiple NDE results. Okay, so let me first show you the current practice for bridge deck evaluation. So I think all of you know this is how we perform chain drag. So you listen, use a chain swipe concrete bridge deck surface and then listen for hollow sound. And hear a hollow sound, use a marker to mark the defect. And then you may need to go back to measure the location and measure the defect area and get a summary estimate the repair workload. So this method has been used for many, many years. Of course, we know there's actually lots of room to improve this current practice, and it is slow, it's subjective, and you don't actually record the data in somehow. And now in digital world, we save almost all our information in computer, but for chain drag, it's still just the mark on the surface. Okay, so this is our solution. We propose an automated acoustic scanning system. This project started in 2015 and finished in 2017. So we developed this system, acoustic scanning system. So let me introduce the main parts. So those are the MEMS microphones. And those are the same kind of microphone you use in your cell phone and using in many electronic devices. So those are the very low cost, the cheap microphones, and each one only costs a few dollars. And so the idea is we use these microphones to replace the human ear. And because those microphones are placed, when we scan the bridge deck, the microphones are placed very close to the concrete surface. So it's only sensitive to the delamination response, and then actually not affected by the traffic noise. And the major improvement from the chain drag is, you notice this chain actually is multiple balls, connected those balls to form a ball chain. And later I will show you. So although there's only a small change, there causes a huge improvement in the signal quality, and includes the multi-channel data acquisition. And we also include the RTK GPS sensor. So this RTK GPS can give a centimeter level accuracy in positioning. Okay, so when we first started this study, so at that time we thought about using the conventional link chains for the acoustic sensing, but then we found the acoustic chains just give too much noise, and then we proposed this new design. So let me show you the video, the comparison with these two chains. So what difference do you notice when you compare the link chain and a ball? Actually, we can put multiple balls to form a chain. So when we drag a chain on surface, is the chain and just slide on concrete. It's really, the excitation is caused by friction. But we know when we want to detect delamination, the hollow sound we hear actually is like we play, let's say, a drum. When you play drum, you tap or hit the drum surface membrane, but not scrape on the surface. So that's why when we change the chain with the ball actually, because the rough surface of concrete, it will jump and impact on the surface. So it gives a much clearer signal and actually much better improve the signal to noise quality. Okay, so this is a result from a test slab in a laboratory. So this concrete slab has 4 artificial delaminations in the depth about from 1/2 inch to 2 inch. So we know the deep delamination will be more difficult to detect. Here, actually, I want to explain, if in the real situation, usually the boundary is less rigid than the artificial delamination. So in the real delamination case, for 2-inch deep delamination, actually is quite easy to detect. But in this laboratory specimen, because it's artificial delamination, the boundaries are really rigid. So when we just use the conventional link chain, and we can easily find those 2 shallow delaminations. But for the 1.5 inch deep, there's some challenge. And actually, because of the rough surface concrete, it causes some false positive result. Then for the deep delamination, actually, it becomes really hard to find either by human ear or from the data. It's really difficult to detect the deepest one. But when we use the ball chain, and clearly the 2 shallow ones are very easy to detect. And for the 1.5 inch deep delamination, actually, with the ball chain, we can clearly see the boundary and almost get the correct dimension of the delamination. And even for the most challenging one, although we couldn't get the dimension, the correct dimension, but we do detect the center of the delamination. So then we develop this, this cart. You can also call this actually is a moving NDE platform. So this one is specifically designed for the acoustic system. So we push the cart, okay, in the middle, here's this microphone, and we use a multiple balls, so it generates many impacts each second. So so far we only tested in the very fast walking speed, and theoretically they can also be mounted on vehicle and scan at much higher speed. Okay, finally, I want to show you a very interesting video that shows the direct comparison of the new technology and the old-fashioned chain drag. So you know the person was in this location when we do the scan in the coming way. And then when we return, almost finish scanning, this person only move a few feet away. So this is a test we did in 2017 in Omaha, Nebraska. So this is a flyover over the I-80 highway, and the total length, I think, was longer than 1,000 feet. And then with this acoustic system, we can quickly finish the scan of this bridge. So that shows the results from this segment and the second segment, and this segment actually in a much better condition. And actually, the visual inspection also shows those two segments have a lot of patches and the potholes. So this project has been, we have completed in 2017, and we applied this acoustic scanning system to many bridges. So next related project is ground penetrating radar. So the reason we cannot just rely on acoustic scanning system is the acoustic system can only detect the near surface defect. So that's for shallow delaminations and surface crack. For bridge decks with asphalt overlay, and most of the times those acoustic methods don't work well because asphalt attenuates stress wave heavily. So far, actually, the only commercial system that can work on the asphalt overlay bridge is the GPR system. The GPR, the electromagnetic wave, radio wave, can penetrate through asphalt overlay and detect internal deterioration. So, but when we apply the GPR, collect data, analyze data, we notice that there's in the current GPR analysis algorithm, there's still a lot of issues and the problems we need to address. Okay, so this project, our main focus is to develop the GPR analysis algorithm. So from a raw image, we develop an algorithm automatically pick all the rebars, extract the rebar reflection amplitude, and then plot the amplitude since we know the location of each scan. So we can just automatically plot the amplitude on the map and then form a GPR scan map. So the major improvement from this research compared to current GPR analysis is we can generate 4 maps instead of a current method usually only generates an amplitude map. So we can generate a surface condition map, and we can generate a wave velocity map that shows the concrete deterioration condition in the cover thickness, and it also gives the cover thickness. So this is the result from a concrete bridge deck in Nebraska. And that shows the GPR amplitude and it's a depth corrected. So this is another improvement we made. So its amplitude is corrected by the rebar depth. And we also show the velocity map. Velocity map indicates the deterioration of a concrete cover. Okay, so after these two research projects, we realized the different NDE results actually provide complementary information about the condition of the bridge deck. So it's better to combine multiple results, but if we just try to do each one result and separately, and each one has a different position, that can make the data analysis more challenging. So that's the motivation to develop a moving NDE platform that can integrate different NDT methods and synchronize data collection, storage, and positioning. So actually this work, there's a pioneering work, and that's the FHWA's Rabbit system. But we probably know the Rabbit system is a very expensive system. And then another thing is, although GPR can go scan at a very high speed, when you put multiple NDE methods together on a robot, the robot can only move at the slowest speed of the slowest the NDE method allows. Okay, so because of this motivation, the UNL collaborate with the Brigham Young University. We propose to develop a low-cost moving NDE platform. And because of low cost, it is possible for many DOT can accept and use this system and to connect the NDE methods they prefer to use for the scanning of a bridge. So this is the general concept. So we propose an open platform that can support multiple types NDE and fast speed, and we can hopefully we can perform the continuous NDE scanning, and we can integrate the positioning, imaging, data collection, and the data fusion. Okay, so this kind of system for each different NDE system, we have a separate computer system, but those are very low cost, a single board computer. And we have a master computer control this slave computer to synchronize the data acquisition. And for positioning, it's also a low-cost LiDAR, and we use this LiDAR to determine the lateral position of the vehicle. So the entire system will be mounted on vehicle. So then we had a demonstration last year in Nebraska. So in that demonstration, BYU demos their patent impedance technology, and UNL demoed the GPR acoustic and high definition imaging system. Okay, so this is the bridge in Nebraska, and those are the results we obtained from the GPR and impedance, acoustic, and the HD imaging. So we noticed those each method provides some, like for those two methods show a high degree of agreement, but acoustic and the image provide complementary information. So currently we focus on the data fusion analysis and from the multiple NDE. So in this research, we also find that the challenge is some commercial NDE system, they do not provide the open data connector. So for you to just you can directly collect data, acquire data, and try to synchronize this. And then we currently also try to work on some solutions for this challenge. And well, at the end, I want to acknowledge the support from Nebraska DOT, and not just the financial support, they also provide lots of help in the traffic control and provides the bridge for field testing. And I want to acknowledge my collaborator, Dr. Mazil and Gusil from BYU, and Dr. Chen Wook at UNL, and actually the graduate students who did all the data collection and analysis. Okay, so that's my presentation.
Perfect. Thank you so much, Dr. Zhu. So for our final presentation, it's by Dr. H.A. Erdemush. Dr. Erdemush is a professor of architectural engineering at the University of Nebraska-Lincoln, specializing in structural engineering. She has a doctoral degree in architectural engineering with a structures emphasis from Pennsylvania State University. Her main research interest is the assessment and rehabilitation of existing and historical concrete and masonry structures. Within this field, she has completed projects related to non-destructive testing, materials research, such as fiber reinforced cements and mortars, corrosion progression and reinforced concrete decks, among others, and finite and discrete element modeling for brittle materials and complex structures. She has authored over 70 technical articles and has served as the PI of numerous research projects, including for the National Science Foundation, Nebraska DOT, and the National Park Service.
Thanks for the introduction, and I'll jump right into it in the sake of time. So my presentation will cover some aspects or explanation of a project that has been going on for a while, about 3 to 4 years, funded by Nebraska DOT. And the presentation, for the sake of time and because those are the completed parts, will focus mostly on the first two phases, and I'll explain kind of how this flowed into it. And I'd like to acknowledge the team, the really large team that worked over the years on this project. Mike Schuler and Donald Harvey are consultants in Atkinson, Noland and Associates. It's a specialized firm. They're experts in non-destructive testing. And they together really, three of us sat down and developed the ideas that started this project several years ago. Eric Garcia was the main PhD student, later postdoctoral fellow, who really dug deep into the theory. And my current master student, Shoaib, continues that work. Several undergraduate students took part, and in the last stage, as we involve asphalt, I brought in my colleague who's an asphalt expert. Probably similar to other DOTs, we also closely collaborate with our sponsors to make sure our research is grounded and meaningful. So I'm really lucky to have the continuous support and technical expertise of many colleagues from Nebraska DOT as listed here. So why did we go into this? I worked on NDT basically from the start of my research career, and the previous presentation alluded to this a little bit also. So it's been a method that's evolving and developing. There's tons of research on it, and the technology improves. But a lot of the methods really are useful after the problem is a really big problem. So we might be all familiar with core results like this. You do an NDT test and you identify a problem. You core, yes, there's a problem, but it's a really big problem already. So eventually you would have to do something major like redecking in that situation. However, ultrasonic testing methods have a potential to dial that identification a little earlier because we're dealing with small wavelengths. So if we can really do our setup and data manipulation correctly, we might be able to detect the onset of the lamination. So looking at nearly visually invisible cracks that can be detected right after they form. So that's really our goal here. And the other issue is most of the NDT techniques are for instantaneous measurements for existing structures, so you don't really monitor the deterioration over time, and this idea has the potential to do that. And finally, we all know, and the previous presentation was a great leeway into that, a lot of techniques are strong in one way and can detect certain types of flaws better than the other ones. So a lot of times the solution is combining methods, but that means either a really complicated system or separate setups for each. And after we dug into phase one, we saw potential that this method can eventually detect different types of flaws with the same setup. So with that, the goal of the starting project was, we had long discussions. All these ideas are great, but you have to start small. So we said, okay, let's see if we can use this to identify the onset of mechanical delamination, which is the physical separation of concrete and rebar using this method. And the how, at the start, we already knew we were going to use amplitude measurements rather than velocity, the time delay measurements that are typical based on some research that was previously published. But the second part of the how came about really as we were working in phase one, that we discovered some research that helped us further develop the ultrasonic guided wave idea, and later the measuring the leakage. And I'll explain this further. So on this slide, you can see the typical ways. On the top three images, you could use ultrasonic testing. The second two, figure B and C, being the most typical. And the last one is what we're doing. So you can find studies, applications, more so on the first three. And what we're doing is the last one in the next slide. I'll explain a little further. Ultrasonic guided waves is the idea where you put the transmitter, denoted by T here, on one end of a straight linear element. We call it the waveguide. And you measure at the other end. So imagine this being a steel pipe. Then you have an expected data attenuation based on one material, and because the impedance between air and steel is really, the difference is really high, most of the energy stays in the steel, and you can go long distances. So this has been used to inspect things like steel pipes in the past work. The second way you can use it is ultrasonic pulse velocity indirect measurements. You can see the picture where your transmitter is on one face of the material and the receiver is on the other face. So if this is concrete bridge, one is on the top of the bridge and one is on the bottom. So there are practicality issues in some cases, but the theory is relatively simple. You have an expected travel time based on the known properties of the material, and if you detect delays with respect to that, you might conclude there are flaws. But as you can see, it would be more spot check of the situation in that particular location. And the third one is very similar in it, but it solves the problem of maybe accessibility of the bottom of a bridge. So your receiver is also on the top, and this time you consider also the reflection of the wave into your calculations, and measure the delay against what you expect to conclude if there are flaws in the way or not. And this would then give information such as there is something going on between where my transmitter is and where my receiver is within that range. And the last one is really what we're doing, and I'll explain this a little further in the next slide. So what we are doing is so it's a variation of the guided wave idea. We put the transmitter on one end of the steel rebar, but we have concrete around it, so the impedance between concrete and steel are closer, so some of the energy does leak into the concrete. So instead of measuring at the end of the rebar, which we would have less of a travel distance, so it would attenuate faster as it leaks, we're measuring through different points on the concrete. So in the cast slab image, you can see we have the ultrasonic transmitter on the exposed rebar sending the signal, and then the wave travels through the bar and we measure through the surface of the concrete. The equipment we used, in the beginning we were using NDE360 platform. Later on we acquired a control group's ultrasonic testing device. So 2 different equipment have been involved. Our sensors, we tried 2 different types. The 2-inch diameter and 1-inch diameter actually have been tried. 54 kilohertz transducers. And initially, we were really excited about these pin inducers. They're really, really small, and they could be embedded and solve some of the practicality issues of the method, which I will talk about later. But unfortunately, the coupling issues of a very small surface to a round rebar and the amplification problems made it not as a good option. So one of the things that I'll conclude at the end, but just to mention, is the technology is not quite there to, the sensors that are available are not quite there to meet the demand of this idea yet. So that's part of our research to kind of investigate what can be done in that. So we started small, as I said, and since we were trying to detect the start of delamination, we came up with a mechanism where we would delaminate artificially where we want it in the lab. So this small slab has a single rebar in the middle. We put a little laminate in that start of that little notch and put 2 plates with threaded rod and washer. So slowly then manually these plates were separated to create a delamination right at the rebar level. We came up with this. We were nervous. Is it going to work? Is it not? To our delight, it did work. So at the first crank, we got a 0.008 inch delamination. We went a little further, 0.016 inch delamination. So every time we took measurements to see, can we see this very fine delamination yet? And we could. And so the top graph here shows our velocity measurements, and the bottom shows the amplitude measurements and frequency domain. So you convert your data. And as you can see in the velocity measurements, you do see a difference. But if you read the numbers, which is what really the equipment shows you, the inspector may be not as confident that a change occurred because we only see a 0.31% change. But when we talk about the change in amplitude, we're seeing 37.5% change and then almost 200% change as the crack width goes higher. So to see that big a difference between no crack to a delamination as small as 0.008 inches, that clearly was really exciting to us. That okay, if you put the sensors in a new deck and measured it in certain intervals, you can really capture the start of delamination. We also then got excited, well, we can probably dial this back and maybe look at corrosion, which I'll talk about in a second. So since we're touching the rebar, some of you are familiar with different techniques, may have had half-cell potential flashbacks. So does the rebar condition affect results? So we created the same specimen with 3 different bars. On the very left, you see the clean bar, a rusted bar, and epoxy-coated clean bar. And the results were great in that we really see no difference between a clean bar, whether it's naked or epoxy coated, but we clearly see a difference when it's rusted. So we can detect chemical delamination, as it's called, or corrosion with this method at the early stages as well, which we later dug in a little deeper. So the very first specimen was small. It was a spot check. Then we cast a larger specimen, recreated that delamination scenario, and looked at different arrays of sensing points to kind of see where we can go. And this was still phase 1. And of course, the measurement gets a little bit more complicated. You need to think about the different types of waves that go into it and how they travel within concrete and the angles they will have. So when you take a measurement at a spot, that doesn't mean the flow is right under it. It'll probably be at an angle. So you have to kind of back calculate maybe where you're seeing that flow. So this shows out of several measurement points that are monitored how we did. Once again, the amplitude readings were much more clear in terms of small delamination detecting. When you see velocity changes, the percent change is very small, so it can be subjective whether that's something wrong or not, but the amplitude measurements were very clear. And the two tables, top and bottom, that is in path of leakage, not in path of leakage, brings up another potential either complication or nuance, I should say, in that if your delamination is in the path of your leakage to the sensor, you would see a different result versus not. So if you can really fine tune this, you might go as far as understanding whether your delamination is at the top of your rebar or at the bottom of your rebar, because there will be a change in how the data reacts to it, whether it increases or decreases. So later we looked at corrosion. We corroded. We tried to simulate a corrosion scenario using sodium chloride solution in basins that were built into the concrete slabs that we cast. We also submerged the whole specimen, and we took data daily up to 40 days. And I'll zoom in here. As you can see, we're clearly seeing it. So visually, we're observing at the edge of the exposed part of it that the corrosion was indeed building as we took our data, and the measurements were changing over time as the corrosion builds. Now, the amplitude is increasing in corrosion measurements compared to the decreased leakage in delamination measurements. Which can be explained as corrosion in the first stages actually improves the bond between the concrete and the rebar. So since you have better bond, more energy can leak into the concrete, so your amplitude increases. Then eventually that will become too much buildup and too much stress, and there will be cracks, and eventually the two materials separate, and that's the delamination. So we were able to detect the progression of corrosion starting very early on. The earliest we report here is 12 days, but we also have like 5-day changes that are already different from that black line you would see. We did, in the early second phase, we also did a brave attempt at a field study. So obviously the bar is not sticking out at the end of the bridge like our lab specimens, and we knew that. So we said, okay, we're going to core, and similar to what is done for house cell potential, and we'll attach to the rebar from one end, and then we'll measure across the concrete. So good news, bad news, the propagation distance was better than we hoped. We could go 14 feet and still viable data. We were measuring every 6 inches. At about 14 feet, 6 inches, the data started getting too noisy. So with this way, that's as far as we could go. And I should mention our longest lab specimen was 10 feet that we could replicate results. So we know we can go up to 10 feet in the lab, and we could go to 14 feet. But the attachment of the sensor to bar does present a problem, we're kind of coming perpendicular to the bar, and most of that energy is lost already, so we can't really fully utilize that guided wave idea. So in the current phase 3, we're working with different attachments, coming up with seats. We recently came up with the idea that we'll have a gypsum little bed, which is one of the better coupling methods we could come up with. Also, I think, again, the sensor technology, I'm starting to collaborate with folks that maybe it's time different types of sensors can help our problem a little bit. So in some summary of results, we can detect onset of delamination as small as 0.08 inch. We can detect the start of chemical corrosion. Good news is that epoxy coating doesn't obstruct the method. And because the leaked wave data reacts differently to different types of flaws, we may be able to not only locate flaws, but also tell what type of, where we are in that spectrum. Propagation distance so far, we are between 10 to 14 feet of usable data. So as far as I'm aware, the early detection still remains the most exciting part of this, which might mean less costly repairs. If you detect the problems earlier, then it's already a structural issue. You might have a smaller repair to avoid the problem from getting bigger. In terms of corrosion detection, it may prove that it's a better alternative to half cell potential, because half cell potential doesn't really work with epoxy coated rebar. And maybe the most exciting thing, you might think, okay, can we do this in all bridges? Is that feasible? That's maybe not the idea, but if we can do this on enough bridges to understand deterioration patterns or the deterioration model of reinforced bridge decks, then really it can be useful for planning, bridge maintenance, and so forth. So as all good research does, we came up with more questions from phase 1 and 2 that led to phase 3 and 4. Practicality is still an issue. We're working on that attachment, and we're getting ready to do some site implementations in the near future. And the other part is really, we couldn't get away from asphalt because Nebraska right now, I believe, as a philosophy, most bridge decks will be overlaid with asphalt after 10 years or right away when they're built. So we're struggling finding naked decks anyway. But also that needs to be considered. So in the current phase, we're looking at the effect of membranes and asphalt on the method, how it will complicate things for sure, but how we can maybe use those to our advantage. For example, if we can figure out a way to detect the problems with the membrane, the rest of it, from what I understand, if the membrane is perfect, we may not have issues underneath it anyway. So we're looking at those things with colleagues at the Nebraska DOT at this time. For those of you who want to dig further into the theoretical aspects or data, we have 2 published papers and 2 reports that are available. And that's it for my presentation. I'd also welcome email questions if there's not enough time here. Thank you.
Great. Yes, thank you very much. I know there was a question submitted earlier, so I think I'll start with that question. And I believe it refers to your finite element model. How does this model correlate to the actual ground conditions, soil/concrete interaction for piles, etc., or soil/metal otherwise?
Right. Well, this is a very excellent question. And of course, this is like a problem everyone is dealing with, is that how we capture these differences in material property and so forth. The method which we're trying to do here is basically we're looking to a change in a signal response of the system, and this change in signal will sum all the variation that's happening there. Well, how much is that? What is how much parameters are there? Could be many parameters, but the idea here is we just capture if there is change in behavior or not. So that's basically the concept, and most people are doing that. Well, what we try to do to make sure we are as close as possible to the real like condition on a bridge, which is really very complicated, especially if talking about all the bridges. We try to when making the model, we really try to get as much as accurate dimension and property of the structure. And this is, we base that on the like initial maps that we have. And then we try to do our best when we create like a physical model is just to use 3D printing and, you know, as much as we can do to make it accurate. And then with the model, we'll do the model updating scheme, and we have to go forward and back between the model and the prototype, which is the rail bridge. So it is, I mean, it's a fair question, but again, there are so many limitations, and you know, as we know, the state of the art, people are struggling with all these challenges.
Oh, great. Thank you very much for your answer.
I have a quick question for Dr. Fernando. And with this virtual reality, when you talking about measuring acceleration and strain, I didn't understand how you do that. Where you put the sensors and how that will communicate with the object.
Hi. Yes, thank you for the question. So what we show on the slides is a sensor which is in our laboratory, where we have a wireless connection with our gate node, and the gate node is being collected. It could be in a laptop. It could be on a station that you have on your bridge with a connected to the internet. So you would need a connection with the internet. It's not a limitation. It's just the way it works, and the data is being streamed with it's called a SQL, where you basically have a broadcast of the sensor data as it is being collected. So it's a real-time data streaming coming from your sensor into your server, and you access from your, you know, with your permissions and on your information, and you can see that in your headset. But I don't know if that answers your question.
No, thank you. That's very good.
Yes. So I had a question for Eugene in Nebraska. I'm familiar with her work. I was very glad to be on the webinar with her. It probably is a little futuristic question, but I think I don't know if there is an interest of having these cell-driven chains or NDE cell-driven, so ultimately you wouldn't have to go on the road with humans, but they would do it individually, remotely.
So do you talk about the potential use with the drone or?
Correct. Yes.
Yeah.
Or robots
some
or
people,
little cars.
Looks like, I think so maybe one person from Canada already tried to use this method, air couples, syncing with the drone. Yeah, we also thought about that idea, just didn't find the proper project to apply. But I think in theory, it is possible.
The other question that I have is a kind of a follow-up. Is there a speed limitation, or what are the speed? Maybe you mentioned what are the speeds that you need restrictions or for your algorithm?
You mean the speed, the upper limit or lower limit?
I was thinking on the upper limit, but I could be curious about both.
I think so. For the upper limit, it's really the resolution issue. You know, I use the 4 balls. The reason I use the multiple balls is if I just use one ball, you know, from the ball jump, then impact, there's a time. If very fast,
Yeah.
that means between two impacts, you have a large spacing. So that's the
Yes.
major concern. Yeah, for low limit, I think maybe if we're very slow, maybe the input energy will be too low. But we didn't have this issue because usually we want at least as the walking speed.
Thank you. Good to hear from you.
Thank you.
Well, very good. I definitely appreciate all the presenters, and your timeliness and time control was perfect. No one went over, so that's amazing. Again, I appreciate you very much for presenting and volunteering your time for this. So thank you very much, everybody. Appreciate you attending. Of course, thanks again to our presenters, and have a great rest of your day.